Hello everyone, today as part of our quadratic expressions unit we're going to factor the simplest kind of quadratic expressions. Remember, quadratic expressions usually have the form of an x squared and an x, right, if x is our variable, and a constant, right, and we usually write it like this, where we have an a, a b, and a c, where a is the coefficient in front of the second degree variable, the b is the coefficient in front of the first degree variable, and then c is the constant. Right. So an example of a quadratic expression would be 3x squared plus 4x plus 2. Right, where a would be 3, b would be 4, and c would be 2. Now, we are talking about simple quadratics. And simple quadratics are just expressions that look, I guess, like x squared plus bx plus c. Or we might say that they are ax squared, where a equals 1. So they're quadratic expressions that have actually nothing visible in front of the x squared. Maybe just really quickly, we'll just remind ourselves that we could have an expression in its factored form. We could have an expression in its simplified form, right? Going from here to here is expanding or simplifying. Going from here to here is factoring. And then more importantly, I'm going to just remind us of the opposite of factoring, which is, I guess we sometimes call it foiling quadratics, right? Where we take these two binomials, multiply them together, and if we do it in one step, right, then we say, well, the two first terms, x times x is x squared, x times 3 is 3x, x times 2 is 2x. I add those two together, I get 5x, and then I get 6, okay? Just maybe one other example, right? If I had x plus 5 times x minus 4, that's going to work out to, well, x times x is x squared. X times minus 4 is negative 4. X plus 5x will be plus x. And then the last two terms multiplied give me minus 20, right? What I want you to notice, most importantly, is the pattern that develops. Over and over in this unit, I'm going to tell you it's all about pattern recognition, right? So, first of all, one pattern I want you to notice right off the bat is this is exactly what we're talking about. These are simple quadratics. How do I know? There's this naked x squared. There's no coefficient there, or really there is, it's a 1, but we don't write it in. Okay, so that means that they will always factor a certain way. The way that they will factor comes from the fact that we can recognize the relationship between what this looks like and where it came from. You will always notice maybe the easiest part, right? This constant, the c value, this one is always the product of what we get when we multiply these two values, right? 2 times 3 is 6. 5 times negative 4 is negative 20, right? So the c value, if we were going to factor something, it's always going to be the product of these two things, right? And maybe we haven't noticed, but this is also just as true. This middle term, this b term, is always the sum of the two numbers in the binomials, right? 2 plus 3 is 5. 5 minus 4 is 1, right? That's 1x. So if I were given the simple quadratic expression with the instruction to factor, here we go, x squared plus 11x plus 28. I would know that that would factor down to two binomials. I can build the two brackets already, right? All I'm doing is working in reverse from what I've done before. And I know that, first of all, the pattern is always going to be x plus something, or, right, it's going to start with x, both of the binomials. What am I looking for? Well, like I said, over here I knew that the n number was always the product of two things, right? So here's my product, 28. Well, what kind of things multiply to 28? Well, I can make a list, right? I could even write it down if I wanted to. What kind of things multiply to 28? Well, 1 and 28 multiplied to 28. 2 and 14 multiplied in 3 to 28. 3, nope, that doesn't work. 4 and 7 multiplied to 28, but there's nothing else, right? So I know that these two numbers here, we could actually call them the R and the S value, will have to be either 1 and 28, 2 and 14, and 4 and 7. Well, how am I going to know? Well, I'm going to know because I know as well that the middle term, that B term, and here it is there it is there, and here it is here, is the sum of those two numbers. Right here, the 2 and the 3 added to 5. Well, out of all of these three things, which two of them can I make add to 11? Well, 1 plus 28 I cannot make add to 11, 2 and 14. 4 and 7 for sure, though, add to 11. So if I fill in that positive 4 and positive 7, if I just plug them here into my pattern, then I know I must have the correct two factors, because 4 times 7 is 28, and 4 plus 7 is 14, right? And even if I still wasn't exactly sure, I could always then take this guy, multiply it back out, and let's see, x squared, and then 7x plus 4x is 11x, and multiply to 28. So there's one example where I had a C value of 28 and a B value of 11. So I needed two numbers that multiplied to 28, added to 11. Okay, let's try a couple more examples. Okay, here's a couple of examples. Again, I can factor these in the same pattern as I've factored the others, because I recognize them as simple quadratic factoring. How do I know that they're simple? Well, they have the quadratic pattern, but it's just 1x squared at the front of each one. Okay, so starting off with this guy here. I know already a couple things. I know that when it factors, it's going to factor out to the two binomials. I know the two binomials are going to start with x and x. I even know this. I even know, because my product, right, this plus 12, since it's positive, well, there's two ways I can get a positive product, a positive times a positive or a negative times a negative. Because I am just looking ahead to what they have to add to, because they have to add to a positive number. Between those two things, I know that my two numbers must be both positive. That's the only way that they will both add to a positive number and multiply to a positive number. Well, if I need to go through my mental list, you can do this in your head or write them down while you're getting used to this. Things that multiply to 12. 1 and 12. 2 and 6. 3 and 4. Done. Okay, there's no other combinations that multiply to 12. Do any of them add to 8? Well, yes. 1 and 12 don't, and 3 and 4 don't, but 2 and 6 definitely add to 8. So I'm going to say that this thing must work out to x plus 6 times x plus 2. Or I could, of course, have written x plus 2, x plus 6. Factors, it doesn't matter what order you do them in. Just like anything you multiply together, doesn't matter which comes first. Okay, in our second example here, x squared minus 9x plus 18. Where should we start? And we haven't asked ourselves yet, but maybe we should. What's the better way to start looking for? I know my two numbers that I'm looking for have to multiply to this and add to this. Which is the easier one to find? And the answer is, it's always easier to find numbers that multiply, right? If I started by trying to figure out, okay, what kind of things add to negative 9? Well, you know, minus 1 and minus 8, minus 2 and minus 7, minus 3 and minus 6, right? And I could keep going, right? Negative 10 and positive 1 add to negative 9. So do, by the, negative 20 and positive 11, right? So do negative 100 and positive 91, right? So do positive 100 and negative 109, right? There's actually an infinite number of things that add to the middle term, right? There's no end to them. So it doesn't make much sense to start looking there. It makes a lot more sense to start looking for things that multiply to the C value, right? So I could make a quick list of that, and I would say, well, things that multiply to 18. Now, I'm just going to talk about positive 18. What things multiply to positive 18? Well, 1 and 18. Again, you don't have to write these down. I usually go through them in my head, but maybe it helps. 2 and 9, 3, and 6. 4, nothing, 5, nothing, right, and 6, then we're back. So we have 3 possible combinations. Now, I'm going to make this point that, again, what do we know for sure? Well, we know x and x. We know that this is a positive product, so that we either have a positive times a positive to give it a positive, or a negative times a negative. Because this b value is negative, we know that these two numbers actually must be minus, right? So really, these are all minus 1 and minus 18, minus 2 and minus 9, minus 3 and minus 6. I just usually kind of look for combinations that will give me 9. Now, out of those 3, the only thing that will give me minus 9 is minus 3 and minus 6. And again, if you had written it x minus 6 times x minus 3, then we get the same thing, right? Check by foiling it out. X squared minus 3 minus 6 is minus 9x plus 18. There we go. The last one, x squared plus 10x minus 24. Okay, maybe we'll just start again with what we know. X and x we know. Now, we know because this is a negative 24, the only way you can get a negative product is when one of yours numbers is positive and one of them is negative. All right, so things that multiply to 24. I'll do the easy one first. 1 and 24, 2 and 12, 3 and 8, 4 and 6, right? So the two numbers that we're looking at are combinations of these numbers. Now, because we remember, though, when we put them together, one of them is going to be positive and one of them is going to be negative, right? So I could actually write in, I could do it double and say, well, it's a negative 1 and positive 24, or positive 1 and negative 24, right? Negative 2 and positive 12, or positive 2 and negative 12. I find that kind of tedious to do. I just end up kind of writing them once and seeing if I can find the combination that works. So, let's see. Things that need to add to positive 10, right? No matter what I do, positive or negative, I can't make 1 and 24 add to 10. 2 and 12. That's interesting. And 4 and 6. That's also interesting. I could do, I could do negative 2 and positive 12 and have them equal to 10 if I added them. I could do positive 4 and positive 6 and make them add to 10. But I know this one can't be the answer because I have a negative here. One of them has to be negative, so it can't be 4 and 6. It must be those two. So it must be x plus 12 and x minus 2, right? It can be, of course, the reverse order, x minus 2 and x plus 12. It may not, however, be x minus 12 and x plus 2, right? That would actually give me x squared minus 10x minus 24. Okay, so here's a couple examples. Just on the next slide here, we'll just give the general pattern. When we have a situation where we can do simple quadratic factoring, we can recognize it because there's a naked x squared here. And we would say that the pattern is always, it factors down to two binomials, x plus, and then we use the letter r to describe what the first one ends in. The second one ends in, we describe s in general. So this is kind of the general form, right, where r times s must equal c, and r plus s must equal b. So this then is just a general definition for the pattern of simple quadratic factoring.